start recording. So this is the first question, but the only thing I would say is that some of the questions, not all of them, have more than one answer, and some of you spotted that. But some of the questions have more than one correct answer. So not all of them, as I said, but some of them. So you may be able to yeah. So that's useful to know. Okay, so I'll go to the next question. So I would say, actually, before, I should have said at the start of this quiz, none of the answers to any of the, other than the first question, none of the answers to any of the questions are stupid. They're all perfectly reasonable answers that could be true of any general message passing system. They happen not to be true of MPI, some of them, but it is, the questions are quite simple, straightforward, but the answers maybe aren't, and none of the answers are stupid. They're all perfectly reasonable answers in general, but we're asking about MPI in particular. I'll just wait for the last couple of people to answer. Okay, so one of the reasons I ask these questions is because there were things that people used to not understand after the MPI course. So I tend to emphasize some of this. Very well done, yes. So a lot of people think that MPI needs special compilers, a special computer, a special operating system, but it doesn't. It just needs special libraries. Well done, everyone got that. That's very good. Why doesn't it need a special parallel computer? That's an interesting point. Why doesn't MPI need a parallel computer? But what do I need to be able to run a five process MPI program if I don't need a parallel computer? Exactly. So absolutely. So as you said, all MPI only talks about processes. All you need to be able to do is to run multiple processes, and any computer, any modern computer can run. Apologies if I keep putting up the same comment, but if people join late, I don't think they see the comment till it appears. Sorry, so you just need to be able to run multiple processes. The nice thing about a parallel computer, of course, is those processes can run on different physical CPU cores and your program can go faster. So that's why a parallel computer is useful, but you don't actually need a parallel computer. Okay, so some of you, if people are doing very well, so let's see the next one. So after initiating the MPI program with Mpi Run -n for my MPI program, what does the call to MPI init do? And again, different message passing systems could have done all these different things, but MPI has a particular behavior. Just wait for a few more students to answer, and then I'll share the answers. Okay, so a lot of people think it creates the 4 parallel processes, and some message passing systems did that, but that's not what MPI does. It's C. It enables the so when you write Mpi Run -n for my MPI program, okay, that Mpi Run command creates 4 processes, and they will just run independently. Okay? So so your MPI run creates 4 processes, 1, 2, 3, 4, possibly running on different computers, and they could just run independently. However, what if you want to do parallel programming, you need to get them to talk to each other, and if they collectively call MPI init, they then discover each other, and then after that they can talk to each other. But it doesn't create the independent program. It doesn't create the process. It also doesn't create the threads. I'm normally not a pedant, but it is important to understand the difference between processes and threads. Although colloquially people use them interchangeably, they're not the same thing. Okay, they're not the same thing. A computer runs multiple processes, and each process has totally different memory from each other. However, within a process, a single process which has its memory space can create multiple threads, and those threads can share the memory of the parent process. So threads can share memory, and that's how OpenMP works with shared data structures. Processes cannot, by default, share memory, and that's why MPI has this SPMD model, single program, multiple data. Each process has its own data. In fact, you could actually I'm gonna, so in fact, I'll just show this because this is quite fun. I think it's fun anyway. I'll just quickly show you. I'll show you my laptop. Give me a second. I'll stop sharing for a second. So just to illustrate how Mpi Run works, okay, here's on my laptop, okay. If I type ls star text, I get that, okay. I could do Mpi Run minus n4 ls star text. I get 4 of them, okay. So, I mean, all the computer did is it launched four versions of ls. Now, of course, they couldn't talk to each other because they never called MPI init. But you know, all MPI Run doesn't even have to run an MPI program. It just launches 4 processes. That's all its job is. So hopefully that makes that clear. Okay, so the next one is, and we've talked about this, but again, different message passing system. If you call MPI receive and there's no incoming message, what happens? The other reason, I should say, the reason I ask these questions is they are commonly misunderstood in MPI. Even people who've developed or worked with MPI programs, I've found often don't understand these things. So I want to have a quiz which covers the very, very basics. Okay, so let's see, show results. So, okay, so most people got it right. The receive waits till the message arrives, potentially waiting forever. And the receive doesn't report there's no incoming message. The reason why this is actually, if you think about it, first of all, there's no timeouts in MPI. MPI assumes 2 things, really. It assumes you've written a correct program, but it also assumes there was no fault tolerance in MPI. If you had designed a message passing system for a computer where there were lots of errors, lots of faults, like a distributed cluster of workstations, if you issued a receive and then no message came for a minute or 10 minutes, you would probably want it to time out because you'd think, well, actually, probably the sending process has died. You know, someone's turned their laptop off. But MPI assumes a perfect program and perfect hardware. I don't cover this in this quiz, but just imagine you had a situation where you wanted to have a receive, but you didn't want it to block forever. You wanted to do some other stuff. So, you know, you didn't know if there, you know, you had a program where you needed to have a receive waiting, but you couldn't afford to wait forever. What would you do? What's the way around this? The fact that MPI receive waits forever. How can you get around that? Well, okay, so timeout in the batch file would be would work against an incorrect program, and yes, so timeout in the batch file would protect you against. But yes, I was thinking about programmatically. Yes, as Mauricio says, a non-blocking receive. So what you would do is you would say, look, you would post a receive and say, look, I'm expecting a message. When it comes, come in here, but go off and do something else. And that's the way that you get around that. But by default, MPI receive is completely is blocking. Okay, so here's a similar question. If you call MPI synchronous send, MPI send, and there is no receive posted, which of the following are possible outcomes? So I'm not saying which happens, but I'm saying which are which are possible outcomes. I mean, one of the reasons why someone said that if there's no message coming in, if there's no message there and you call MPI receive, MPI might report no message. MPI has to be robust against processes running at different speeds. And so it's actually very difficult to know when you post a receive if there's a send coming, because the sending process might be having a bad day and be slow. So in some sense, to be correct in all situations, MPI receive has to wait forever, because in principle, the sending process could be running infinitely arbitrarily slow. So actually, if you think about it, if you want your program to be correct and match its sends and receives regardless of the speed at which the process is run, and remember, you have no control of the speed at which a process is run, then it has to do that. Okay, so okay, again, most people, I mean, D is possible for other methods, but MPIS send is like making a phone call. So the send waits until the receive is posted, again, potentially waiting forever. And the reason why that is true is because it's S send and it's synchronous send. Okay, so that's the reason why it's like making a phone call. Again, there are no timeouts. Again, if you designed MPI for a system where you were worried about hardware failures, if you issued an S send and there were no receive for 5 minutes, you'd want it to come back to you and say, "Are you sure? Maybe the other guy's gone away." But that's not okay. So it's a bit more difficult here. If you call MPI asynchronous send, the MPI send buffered send, and there's no receive posted, which of the following are possible outcomes? So I mentioned that people tend not to use buffered send, the asynchronous send, for sort of technical reasons, but it is there, and you do need to know what it does. Okay, so if you don't know, just have a guess. It's anonymous, as I said. So I'm equally interested in the questions, the pieces that get wrong, because that means I haven't taught it very well. So it's very okay. So I never understand how it reports the percentages but most people seem to have got so. See, the send waits until receive posted, potentially waiting for it is not true, because this is asynchronous. So a buffered send is like sending an email. So that's why it's called asynchronous. There's no synchronization. So both D and E are possible. D, the message is stored and delivered later on, if possible. And that is because it's buffered asynchronous. And the corollary of that is F, that the sending process continues execution regardless of whether the message is received. However, you'll see that B is also a possible outcome. Now, actually, when I first ran this quiz, I didn't have B as a possible outcome, and someone pointed, B is a possible outcome. So why is P? You've called MPI B send, and the send fails. It actually says it can't do it, and it crashes, and your program stops. Because when MPI gets an error, it always crashes and stops. It's rather annoying. Does anyone can anyone give me an answer as to why? Absolutely, there's not enough memory to store the buffer. And that is one of the problems with MPI send, that you can get programs that crash unpredictably, because one day the receiving processes are awake and they receive the messages and the buffer doesn't fill up, and another day the receiving processes are a bit slow. Your out box, as you can imagine it, your post box fills up and the program crashes. And remember, MPI send is up to you, with a rather nasty call MPI buffer attach, to tell MPI right at the start of the program, I'm going to do buffered send. Here's a megabyte to store the messages. But in some programs you can reason an upper bound on that, but some other ones it's more difficult. So yes, exactly. So that's an interesting to know. Now, okay, so this is the explanation. Now, the next question sounds quite difficult. So same question I've asked about MPI send, MPI B send, now MPI standard send. If you call a standard send MPI send and there is no matching receive, which are the following possible outcomes? And this is one of the trickiest parts of MPI. As I keep saying, if you don't know, just take a guess, because, as I said, everyone's interested in what people think, and it is anonymous. Some people don't like the fact it's anonymous because they like to get their score at the end. I've never found a way to do that. I still not entirely know how Socrative reports answers when there are multiple correct answers. So anyone, if you don't know, just have a guess. If there's a few people still to answer. Whether it penalizes you for wrong, I'm not really sure. Okay, so we've had most people answer. So let's look at the. So this is very interesting. So again, so MPI never has messages disappear. By disappear is sort of just, a sent message has to be received, because we're correct. So and there are no delays. So the send doesn't time out. So the important point is that MPI send can be synchronous or asynchronous. So that means it can act like S send or B send. So you would think that the correct answers to this question, given that MPI send can be either S send or can be either synchronous or buffered, would be the union of the correct answers. So yes, if MPI send decides to be synchronous, then C is true. The send waits until the receiver is posted, potentially waiting forever. If MPI send decides to be asynchronous, it would store the message to deliver later on, and therefore the program would continue execution. However, B was a possible answer for B send, but it's not a possible answer for send. Why is that true? So absolutely. So in fact, the point about MPI send is precisely to avoid B. So MPI B send says, David has required me to do a buffered send. There's not enough buffer space. I can't do it. I have to give up. MPI send says, David has asked me to do a send. I'll try and do it asynchronously as buffered, because that's probably the most efficient thing to do. Oh dear, I've run out of buffer space. I won't. I'll just take the safer option and wait. I'll wait for the message to be received, and maybe by the time the message is received, some other message passing is taken on and the buffer is emptied a bit, so you're okay again. So this is quite a tricky one, actually, and it's important to understand what's going on here. I think I've just basically. The important point is now in principle, MPI is allowed to decide whether the MPI send is synchronous or asynchronous arbitrarily. You can decide on the day of the week whether the message length is odd or even. Okay, You are not allowed to assume anything about it. However, in practice, what MPI does is it uses it as an opportunity to send small messages in an asynchronous way and not hold the program up, but be safe and send large messages in synchronous mode. Now, there is a threshold which is typically, I don't know, 10 kilobytes. But you cannot. That will vary on different implementations. So on your laptop, on Archer, on Cirrus, our other system, on any other machine, in fact, that threshold will depend on the number of processes you run on. The more processes you run on, the less memory MPI has to play with, and that buffer will probably get smaller. That threshold will get smaller. So you cannot assume what the threshold is. Your program should work correctly with any of these thresholds, but there will be a threshold. It's very easy to find out what the threshold is. Just write a ping pong. Just have two processes send a message to each other at the same time, which will block if it's synchronous. Increase the buffer size till it stops. I mean, I've done that. Or you can look up the manual. Okay, as I said, if you have any questions, go. Right, next one. The MPI receive routine has a parameter count. What does this mean? Again, I think I discussed this, but it's not obvious at all. So we only have 40. Sorry, I misread 40 answers. Sorry, apologies about that. I misread. So let's see show results. So okay, so just a brief to discuss this, because again, this is a so it's not C or A. MPI tries not to talk about bytes. It rarely talks about bytes because MPI tries to be portable. And whenever you talk about bytes, you have I know C programmers love to talk about bytes. Whenever you talk about bytes, you have a non-portable program because two computers can use different numbers of bytes to store an integer. So now, most people think it's B, the size of the incoming message in items, integers, but it's actually not. It's D, the size of the buffer you've reserved. When you do an MPI receive with count equals 10, you're telling MPI, I'm expecting a message, and I have reserved enough space for 10 integers. Now, in many programs, all your messages are the same size, and so it will in practice be B. Okay, often it is B because you know, but in principle it's not. MPI is designed to allow you to receive messages of unknown size, so it's not. It's D. Now, so in practice in your program, B may be true. Actually, it's D. You're just saying I want to receive a message, and by the way, I have reserved, say, 10 integers for it. Okay. So then the obvious question everyone asks next is, well, what happens if the incoming message is larger than count? Sorry, I'm having a little bit of trouble with my audio visual here. So sorry. So we've got everyone answered. So results. So okay, so this is very interesting. This is pretty the first one where more people have got it wrong than right, although it's not obvious. Okay, so it's actually A, the receive fails with an error. Now that's very interesting because D seems like a perfectly reasonable answer. So the reason why, so the question you have with, imagine D were true, okay? I say, I would like to do a receive, and I have a buffer for 10 integers, and 15 integers come in. And so the first 10 integers are received, okay? What would happen with the other 5 integers in that case? Anyone have so that's sort of the question you have to ask. What would happen with the other 5 integers? So you'd have to be notified that the message was too large, and you'd have to then issue another receive, I guess. The reason why it isn't D is that I think maybe if people have more of a networking or computer science background, they think of message passing as being a pipe, where you put data in one end and receive it at the other. And in that case, this is exactly what would happen. You'd shovel data in one end, and you would receive it, in whatever chunks you could cope with at the other end. Okay. However, MPI's message passing, MPI relies on precise matching of a sending message to a receiving message. So the data is either received in its entirety or not at all. And so that's why MPI says MPI says, look, I want to match messages. I have to match a sender with a receiver. A sender, a receiver, match them up, and it's all over. There's no residual data. There's no memory. Done. And so that's why MPI. So is that clear? I mean, this is the one where, yeah, I think people maybe who have different backgrounds often think that D is a natural thing because they think of more of a continuous pipe model, where MPI is more of a discrete. Does anyone have any more questions about that? It's interesting. So obviously the next question is fairly obvious. What happens if the incoming message is, and someone asked this and I said I would not answer it until we did the quiz. Okay, so we've got everyone answered. Let's see what the results are. So, okay, so the receive fails with an error. So, okay, so no. So MPI is designed, as I said, to allow you to receive messages where you don't know the size. Okay, so it's not A, because you actually want to be able. There are situations where you need to have a correct program, where you need to. It's useful flexibility to have. So the first 10 items are received, but the first 10 items are received, but the rest of the storage is not zeroed. So it's just received. And people often ask why that is. I can think of 2 reasons why that is. First of all, you can imagine situations where you have a buffer, an array you want to receive into the middle of the array. You want to say, okay, there's 5 new entries. I'll overwrite them and not zero all this stuff. I think the real reason is performance efficiency. I don't know if you know much about modern hardware, but reading and writing to memory is fantastically slow. Okay, zeroing an array is about the incredibly slow thing to do. memory is appallingly slow. So imagine I had a 1 megabyte array, and I received one integer or 1 byte. I'd be a bit annoyed if MPI went away and spent, several milliseconds zeroing the other 999,999 bytes. So it's really, zeroing memory is a very expensive thing to do. Although you may not think it is, you often think it's a very, very slow thing to do. Setting arrays to 0 is horrifically slow. So so you don't want to do it. So I think it's really for efficiency. So yeah, RAM is slow. RAM is, I mean, how fast is your RAM? It's your processor, which is clocking at several gigahertz, can process data 100 times faster than it can read it from memory, probably. I mean, memory is spectacularly slow. It's tens or hundreds of times slower than we need it to be to keep up with the Now, of course, it's not that bad in practice because we have cache. So small array, so cache memory is fast, but memory is at least an order of magnitude, if not 2 orders of magnitude, too slow to keep up with the speed of modern processors, which are clocking at where we have multiple CPU cores clocking at multiple gigahertz, and can do multiple operations per floating. I mean, it's just, yeah. The speed of memory is the biggest headache in high performance computing. Is that okay? Does that make sense? Okay, so so the explanation here. Fine. So okay, so I've issued a receive, and I've said count equals 10. MPI, the receive has returned, but technically all I know is a message of 10 or fewer items has been received. But then, now in some programs, I know all the messages are of size 10. But if the message could be of a smaller size, then I say, well, I clearly need to know how big it is. How do I actually find out what size the message is? So how are we doing? Yep, so we've got a... Okay, so so MPI can tell you. If MPI couldn't tell you, then it would be difficult to write a correct program. You could store it in the tag. So yeah, MPI does need to be able to tell you, because otherwise it would be difficult to write a correct program. If MPI is saying that I will allow a smaller message to match a large receive buffer, then as a programmer, you need to know. If MPI couldn't tell you, you'd say, can I receive a message, please? I've got a buffer of size 10 integers. A message comes in. You would then not know which of the data was new and which was old. All of it could be new, all of it could be old if the message was 10 or 0 long. You could use the tag, but you could specify, you could use the tag, but MPI but what MPI stores it in the status parameter. MPI stores it in the status parameter, which allows you to retrieve the size of the income. Remember, the status parameter gives information on the actual message that was received. And so if you did a wildcard like MPI any source, it would tell you who it actually came from. If you did a wildcard like MPI any tag, the status, but it also tells you the size of the incoming message. Because in some sense, you've wildcarded on the size, although with an upper limit, I guess. People now always ask, okay, so to write an MPI program that works, you have to be able to have an upper bound on the size of the messages. Otherwise, no matter, you could always get a bigger message coming in. So what happens if you? So I did discuss this very briefly. But if I want to be able to receive a message of an arbitrary size, I need to know what the message size is before I issue the receive. So I did mention this very briefly. Can anyone? There are other ways that you can do it manually, actually. So how could I guarantee to receive a message of arbitrary? So assuming it fits. When I say arbitrary, I mean arbitrary. When I have to specify a count when I do the receive, but I don't know how big the message is. There's a couple of ways you could do it. Yes, so the naive way to do it is to do two sends. Always send two messages. The first message is a single integer with the size of the following message, but that will be very slow because sending a message is a very slow operation. The right way is, as Michael says, that so there's a routine called Mpi probe. An Mpi probe does everything that Mpi receive does except receive the message. So Mpi probe has all the parameters of Mpi receive, except it doesn't have the receive count and the receive buffer. So what you would do if you don't, you would do an Mpi probe saying, if I were to issue a receive here, what would the message be? Who would it be from? How big would it be? That information will be stored in the status. You then query the status, malloc or allocate the array, and then receive. Okay, so that's good. Yeah, that's good. That's the correct answer. The next question is, okay, so MPI output always is a bit, can you see all that? Yeah, so the question is, I've got a piece of code which does welcome and goodbye because they've got the same number of characters. Which of these are possible outputs from a program which prints welcome then goodbye? Hopefully that's all on the screen. Yeah. I'm just dashing. I'll be 2 seconds while I get myself a coffee. So I apologize. Okay, so I've had 12 answers. A couple more people just have a guess, as I said. Okay, so let's look at the results. So, oh, very well. Okay, so almost everyone got it correct. So that's very good. I mean, output is difficult in MPI to understand. So the correct is that A, B, C, and D. Why is B not possible? If I just get that. So why is B? Goodbye before welcome from rank 1. Yes, that's correct. So rank 1 says a welcome for goodbye. So when MPI, can you see my camera still? So I because I get a different view. You can still see my camera? Can you? Yeah, okay. So when you print results from two processes in MPI, they're printing to, remember, one of these processes is on my laptop, the other one is on my colleague's laptop, on her laptop in Australia, okay? So it's actually the Mpi Run program which connects to the output streams of these processes and brings them all together. But it brings all these output streams together. Luckily, it doesn't merge them like that. You very, very rarely, unless something goes wrong, get output merged on a line by line basis, and then that would be hello go from rank. That would be really hard to read. It merges them on a line by line basis. However, it could merge them like that, like that, like that, in any way whatsoever. So the order, the mutual ordering between two processes of lines in the output has nothing to do when they actually run. However, it does maintain the ordering of each individual process, which can be useful. And so, for example, some people say, well, what I'll do is I'll flush the buffer. I'll flush the standard out. Who knows what flushing does? I mean, that flushes the buffer on my colleague's laptop in Australia. What does that mean? Flush it to where? I mean, I really don't know what that. So it, you know, it's very hard to understand MPI output. It can be quite difficult. So I think you understand the explanation here. And there's a lot of buffering going on between the printing and the output, so who knows what order it ends up in. So we've got two more questions. So this is a slightly, this is one which is slightly sort of challenging. So for I equals 0, I less than size either or plus. If rank equals I, print hello from rank whatever, and then, you know, what do you think about that piece of code? Again, you've not written many MPI programs, so it's quite a tough question, but I'm trying to get across a point here. Just have a guess if you think it's interesting, because it's not easy. Quite a tough question, and we can discuss various options. Let's wait for a couple more people to answer, then we can discuss it. Okay, okay. A lot of people think, hey, the for loop ensures the operation is in order in time, right? So why is that not true? So that's something which is it's very that's kind of the obvious. That's what a lot of, that's why I asked this question. That's the thing you would naturally think. Why is that not true? Exactly. The loop is run each process in parallel. So each process is independently running this, and they could be running at different times. I could be running this loop today, and the process in Australia could be running this loop tomorrow. So there's no such thing as a parallel loop in MPI. This is not a loop across processes, it's a local loop, okay? B, the for loop ensures that operations are done in parallel across all processes. You'd need something like that if this was OpenMP, but in MPI, this is done in parallel by default. So that's why A and B are not true, although in other programming models or parallel models, they might be true. They're not here, okay? And what it's not D, the final value of J will be equal to tail times on all processes. That would require j to be a shared variable. Okay. Now, remember, j is not a shared variable. There's no shared variable. So the j is different on each process. So why this is entirely redundant is I don't. I mean, just you're doing very well, so you probably understand this. But I think, for example, imagine I'm in a room of 100 people, okay, and we all have a number. I'm number one. There's number one, number two, number three, number four, number five. So I have this big list, okay, and it has. Sorry, everyone in the room has a number. You're given a list, okay, and there's 100 people. There's a list down the side which has 100 entries, and then there's your name by it, okay. You could say, everyone, look down the list, okay, and if the number matches your number, do the operation. So I say I'm 13, I equals 1, no 2, no 3, no 4, no 13. All right, there's 13. Then I'll read out my name. My name's David Henty, okay. That loop is entirely redundant because everybody executes the loop, but because you have the if rank equals I, the actual operation is only performed on one process. Now, there would be a way. So, okay, that's exactly what I was going to ask. There would be a way, okay, to achieve that. So, where would you put the barrier? Okay. Well, what you actually want is, I think, don't go on the before. You want basically before the if or at the end loop. Yes, I would do it before the if. So basically, everyone loops. So everyone, we say, right, everyone stop. Okay, one person does something, then we move on. Now, that would not ensure. So it would ensure the operation is in order in time. However, it would not ensure that the print statements appeared on the screen in the right order, because unfortunately they could still disappear. However, when this is useful, and the only time that this mode of programming is useful is if you want sequential access to a file. There are better ways of doing it, actually, but imagine you said, I've got a file, okay? Unix doesn't support multiple process accessing files. What I want to do, I want in turn a process to open the file, append to the file, and close the file. I want to do that in turn, okay? Then you could do this. For I equals naught, I less than size, I double plus, MPI barrier, if rank equals I, open, append, close, then do it. So that would then work. So that is the only time I've used this idiom of programming. But you do see in a lot of people's programs, and they misunderstand. And often their program works because what they think is that they're doing it to ensure that the loop is executed across all processes. They don't realize that actually. So this is entirely equivalent to this statement here. Print hello from rank j equals 10 times rank. That code there is entirely equivalent to that code, assuming that rank is set to your rank. Okay, now I haven't told you that, but assuming that rank has been set to MPI com rank, then that's true. Okay, I've got one final question about collectives. So this is formatted very badly. So apologies to the Fortran programmers. I appreciate this is in C, and the formatting. I did format this correctly, but the systems was used. So what is the output of this MPI code? Sorry, apologies for the formatting. Running on 8 processes, i.e. rank 0, 1, 2, 3, 4, 5, 6, 7. So let's read it. So the even processes, if rank % 2 equals 0, call an MPI on reduce, and their in buffer is rank and their out buffer is even sum, and one even process, rank prints even sum equals this, and the odd processes do the same command MPI on reduce of their rank, but they place the answer into odd sum, and then rank 1 prints odd sum equals this. So hopefully that code is clear for C and Fortran programmers. Apologies for the formatting. They keep updating this system, and every time I run it, it formats differently. So, but hopefully that's legible. What do people think the output is? Just to note, the sum of the first 7 and 8 integers is 28. 0 plus 1 plus 2 plus 3 plus 4 is 28, just as a hint. And if you don't know, I said just guess. It's fine. It's all anonymous, which is why I like this quizzing system. So wait for a few more to come in. So just as I said, it's actually not, well, it's not a trivial question. It's not a straightforward question, but wait for a couple more people to answer. It's very hot in here. Unusually for Scotland, it's very sunny at the moment. Okay, so we've had quite a lot of good answers. Let's see what we're saying here. That's fine. Okay, show results. So, okay, so the obvious answer is, I think someone just got them the wrong way around, is C. Even sum is 12, odd sum is 16, because the sum of 0 plus 2 plus 4 plus 6 is 12, and the sum of 1 plus 3 plus 5 plus 7 is 16. However, the right answer is actually B. B. I mean, the code is, so this is kind of a trick question. The code is written to make it look like the answer is C. I appreciate that. This is the only question I have here, which is something of a trick question, but some people have spotted the trick. So absolutely. So why is it called by all process? Exactly. So the important point is that the com is com world. Okay. So when you call the statement about collectives is all processes have to call the collective. Okay. So all processes have to call MPI or reduce. So I've specified com worlds here. So all processes have to call it. However, they don't have to call it from the same line of code. Now, normally they are, okay, but they don't have to. In fact, how can the library know? If you write a library, okay, you're writing MPI or reduce. You say, right, okay, rank 3 is called MPI or reduce on MPI com world. That means I need to wait for everybody else to call it, okay, because it's on com world. Fine. I don't know what line of code they've called it from. I'm a library routine. I just get people calling me. So in fact, this line and this line match each other, okay? And the only difference is that so they all get the same answer. They're all adding up all the ranks. The only difference is the even ranks choose to store the result in something called even sum, and the odd ranks choose to store it in odd sum. So as I said, it was a trick question in some sense, but a good number of you spotted the trick. How would you actually how would you get C? How would you get the even processes and the odd processes to actually participate in different reductions? Because you might want to do that. So how would you? Yes. So absolutely. So you would have to put all the even processes in the even communicator and the odd processes in an odd communicator, and they would each call MPI reduce on their own subcommunicator, for example. And so you can do that, but it's not what this code does. So hopefully that's my last question. I hope you found that useful. I hope you enjoyed. As I said, I try and explore issues which are commonly misunderstood or not taught, or maybe I don't teach them properly. So I'll finish the quiz. I can look at the activity. I don't understand what this means. Well, it's anonymous, so you know, I don't. It doesn't really matter. I'll end the quiz. So, okay, so I don't know what I'm doing now. Okay, so I've done something a bit stupid here. Right, sorry, so I will now stop sharing. We are on time, remarkably for me. So fine, so that was the MPI quiz. Now we're doing a practical and then a break. What I will do is I'll take a 5-minute break and we'll come back at maybe take 10 past. So the practical carries on before and after. I just want to introduce the practical. So what I used to do is I used to introduce the practical. There was a long session for you to work on it. Then I gave my tricks and tips lecture. But I felt it was better to do it the other way around. So what I will do is basically introduce the practical. You can do with it over the break. You can play with about with it over the break if you want. But then we'll have a coffee break, and I'll come back and give my sort of tricks and tips lecture at 11. So let's take a break because I probably put you onto coffee. So I get doubly confused because it's not only are we teaching in British time and mainland European time, but between last week and this week we've gone from GMT to BST. But I'm sure that so we'll be back in apologies if you can't see the whiteboard. All I put up on the whiteboard is a little message saying back in 5 minutes. I don't quite understand why that's not working. That's strange. At least the audio is working, which is much more important. So as I mentioned in the email, which hopefully you got. Actually, can I just? I've never used the email facility before. So did people get an email from me last night? Yeah. Okay. So that's nice. So one of the nice things about all of you being in a separate project, TA057 for this course, there are two benefits of it. One is we can let you have access to the accounts for several weeks after, because we can identify you and we can close the wall at the same time. But it also allows us to use the functionality. I'm the project manager of that group, and it means I can email all that's okay. That was useful. I've not used that functionality before. Fine. So what I wanted to do here was to come up with an example, which was, as I hopefully explained in the email, simple enough to get to grips with in a day. I'm not saying complete, but to get to grips with, but also complicated enough to represent a reasonable range of MPI functionality, and also to be representative of the kind of simple parallel codes you might come across. So I did an image processing example. The reason I like image processing is you get nice pictures out at the end, which is useful, but also it does allow you to visually debug. So if I have an image, okay, and I make a mistake, I can see that some of the image is wrong. Okay, so I can actually see, so you can sort of visually debug, which is nice. So what I'm going to do is I'm going to do a domain decomposition. Now the parallelization of this problem is identical in concept to the parallelization of the traffic model. We split a domain up amongst processes, and we have to do halo exchange between neighboring processes. The difference here is that it's actually a 2D array, not a 1D grid, a 1D line. And a 2D array is much more representative of real scientific and technical process. Imagine weather forecasting. You'd have an array representing the land. A lot of problems. 3D as well, but 2D is much more representative. So we're going to start with a big array, which will represent an image. Okay, so I have pixel values in it. We're going to split it into pieces. Here I said 3 pieces. We're going to assign the pieces to processes: process 0, process 1, and process 2. And then we're going to have an update scheme. The image processing algorithm will have an update scheme with the value of each pixel at each iteration. It's a multi-step thing. We do many iterations. At each iteration, the value of a pixel depends on itself and its nearest neighbors. Again, the same as the traffic model. Okay, to update a cell in the traffic model, you need information about yourself, are you occupied, and your nearest neighbors up and down. The only difference here is that you need information about yourself, your own pixel, and the 4 nearest neighbors. Okay, up, down, left, right. Now that means that we're going to again use the same trick. We're going to use halos. So for example, if you just look up here, if I'm updating pixels in the center of the domain here, it's easy. But if I'm updating and it's also easy here because I know left and right, it's fine because I've split the domain only in one dimension, and that's a choice. Okay, we can discuss which dimension later on, but I've split it here horizontally. Updates in the horizontal, but if I want to look at the pixels up and down, I have a problem because here the down pixel is owned by this guy, and she's updated it. And here the up. So what we're going to do is the same trick as before. We're going to extend the arrays with halos, but here the halos aren't single values; they're entire lines. And what we'll do is the halo here, which is this here. So I can still update all the pixels in the core region. To update, let's look at process 1. To update the values here, this is now a bigger array. To update that value here, I need. So what will happen is that all the values from this entire line of pixels from process 2 is sent to process 1 and placed here, and this entire line of pixels from process 1 is sent to process 2 and put there. So this is identical to the halo swapping we did in the traffic model conceptually, except we're sending a lot of data, potentially, not just a single value. And so what we'll be doing is we'll be swapping the halos, doing the update. But of course, once process 1 does the update, these values are changed. So we need to swap the halos again. So we're having a communicate, calculate scheme. So that's what we're going to do. So what I'm going to do is I'm going to do an example based on edge detection. So what I'm going to do is I'm going to give you a very simple algorithm for edge detection, which takes an image, and here I've got an image of, let's do a poll. This is a picture of Mel Gibson in Braveheart. I've not seen Braveheart. Interesting to see. I've not seen. Okay, so most people haven't seen it. Okay, that's interesting. That's interesting. It's a film about William Wallace, who was a very famous Scots person in the late 13th century. I can say this because I was born in England, but he does something which makes you very popular in Scotland. He killed lots of English people. It was a long time ago, though. He came to a sticky end. Anyway, I don't use this image in the exercise because someone asked me if I had copyright for that image, and I don't. But anyway, so what I'm going to do is, yes, he did have a very bad accent in the thing. So you can do edge detection on this image, and in a single pass, you can go through the image in a single pass and produce a bunch of edges. And you can see that actually looks quite good. You can see the outline of Mel and his sword. That's quite good. However, we could parallelize that algorithm, but it wouldn't be worthwhile because you'd read in the data, you'd scatter it to all the processes, they'd update their image, then you'd spend all your, it's just not worth parallelizing that. However, it turns out that if I give you the edges, you can reconstruct the image. It's not obvious, but you can. And that requires hundreds of iterations. It's a slightly fake thing to do in this context, but it's quite fun. I give you the edges, and you have to reconstruct the image. And that takes hundreds of iterations, and that is worth parallelizing. Okay, so that's why I do it. So the edge detection is going to be very simple. We compare a pixel to its 4 nearest neighbors. So the pixel values are between 0 and 255, and we declare the edge to be the value of the image to the right, up, left, and down minus 4 times the image. In other words, we define the edge to be the difference between the average difference between the image and its 4 neighbors. Okay, if you look at this, okay, so we're computing the difference between the 4 nearest pixels and the current pixel, and you can see that that means that if the pixel values are constant or changing linearly, you don't get an edge. But if they're changing rapidly, you get, and that works quite well. You'll see we get negative values because you can get negative edges. But I do some processing to make sure negative values don't screw up the image. So anyway, that's quite nice. Okay. What about you asked about the boundary conditions? Well, we'll use non-periodic boundary conditions. So pixels off the edge of the image are set to white. So what we will do when we write the serial code, okay, we will pad the 2D array with halo. So even in the serial code, we will pad the array to be one bigger all the way around than it needs to be, so that when we look off to the right of this pixel here, there is a pixel here, and its value is white, which is 255. And so we do that. So even in the serial code, we have halos. So all halo, but in the serial code, all halo values are set to 255, i.e. white. In the parallel code, some of the halo values will be updated from the nearby processes, but we have halos in them. So some of you may recognize that is just saying edge is the second derivative of the image. This is a simple representation of the second derivative in 2 dimensions. So if you can switch off the next 2 minutes if you don't have a physics, maths, engineering background. But actually, okay, we have actually defined that the edge is the second derivative. We've defined edge is grad squared image, and what I'm doing is I want to solve, given the edge, I want to solve grad squared image equals edge. Okay, and what we're going to do is we're going to use something called a Jacobi solver to undo the simple edge detection algorithm. This is a simple example of discretized partial differential equation with nearest neighbor interaction. So in fact, although perfectly willing to view this as a kind of an exercise in slightly contrived image reconstruction, image processing, actually, if you're a physicist, mathematician, engineer, you can say this is actually solving the Poisson equation, which is a very common, embarrassingly common equation in science and engineering. So what is the algorithm for? And you can see that defining the edge to be the second derivative of the image is a sensible thing, because if the pixel values are constant or linearly changing, there's no edge. But if there's a gradient, that looks like an edge. So that's fine. So how do you, given the edge, how do you reconstruct the image? Well, you have to trust me, but what we do is many times, we take an initial guess. We have an old image, which is just some guess, and we update it many times, saying the new image is a quarter of the old image to the right, up, left, and down, minus the edge value. And then we repeat that many times. Okay? And you have to trust me, but that actually reconstructs image from edge. It gets you back to where you started. It's not obvious, but it does. It's quite easy to convince yourself that actually, when you reach the image, you stay, because if I have the image, then this equation collapses to new ij equals old ij. So when I reach the solution, this algorithm will stay there. It's not obvious that it gets there, but it does. It's called the Jacobi algorithm. It's incredibly naive, but it's okay. And in parallel, we have to update the halos from neighbors every iteration. So the domain decomposition. So I'm going to draw. People aren't going to like me for like this, but I'm going to draw the array so I goes along and j goes up. Okay. Some people like to draw things as matrices. I goes down, j goes along, but these aren't matrices. These are images. So I'll draw it like this. In C and Fortran, it is in C, it is most convenient to split the images in the first dimension. In other words, everyone has all the j values for a particular I. In Fortran, it is easier if you split the array the other way, that everyone has the same, all the I values for a given j. Can anyone, there are 2 reasons, one maybe not so obvious, one possibly a bit more obvious, why are these best decompositions. You could split the C version across the second index. Yes, that's exactly it. The location info in memory. Do you want to expand on that? That's exactly where you. That's exactly the right answer. Do you have a? Do you want to expand on that? I mean, that is exactly the right answer. So what's contiguous? You've hit it right on the head. So there are two things which are contiguous if you do this. The slices, yes. So I think you've got it there. So there, if you do it this way, then when you exchange data, okay, all the data in the halo is a contiguous block of memory, okay, a single block of memory in C, because C and Fortran disagree over whether it's I or J, row or column major, if you want to call it that. But in C, all the J values are together for a given I. So when we do halo swapping, we can send and receive the entire slice of pixels with a single message. We just do a single message of length n, or in Fortran, a single message of length m, and we can send and receive all the pixels at once. The second reason why the fact is contiguous in memory is useful is it means that to distribute and gather these arrays back, we can just use Mpi gather and Mpi scatter. Remember, gather and scatter take a linear array and chop it up into linear boxes. So remember, a 2D array is really just a linear array of size m times n. Scatter will send the first m times n over 4 entries to the first process, the second. If you split it up this way, they correspond to these slices. So there are two reasons why this is good. A, it makes halo exchange easier because you can use a single send and receive. We don't need to use vectors for non-contiguous access. And secondly, you can use gather and scatter for scatter and gather for the distribution and collection of the arrays. It makes things much easier. So yes, so you know, I'll explain this more in the next, but basically, okay. In C, are you a C or Fortran program, Michelle? Okay, so in C, if you do int, let's do double x of m n, yeah, then x of m, x of I j x of ij is next to x of I in memory. So when you do it, there's no such thing as 2D arrays. Okay, you define the 2D array, double x mn, you just get a big block of m times n doubles. But there's a mapping between xij and this linear array. And the mapping is such that in C, xij plus 1 is next to xij plus 2. So that means if you want to send ij plus 1, ij plus blah, blah, blah. They're all next to each other in memory, so we can send them as a single message. Remember, MPI can only send, standard MPI send just sends a block of n doubles, okay? You can MPI send buff, send count, send type, okay? If you wanted to send xi plus 1, xi plus 2, they have a stride, they're separated by n, and you would need to use a vector, and that's just a bit more complicated. So it's to do with the fact that a 2D array is just really a 1D array, and there's a mapping, and the mapping, and Fortran and C disagree. No, but you're thinking of it being a matrix ij. I have written it. I goes along and j goes up. Yeah. So I know this would look different if you drew it as ij as a matrix, but I've not drawn it as a matrix. Yeah. I could go into y for many philosophical and there's actually there are okay, but so the reason I think it's stupid to draw things, so the reason I think it's stupid to draw things as matrices, okay, ij, okay, is that let's look at the Fortran value. If you do this as ij, okay, then yeah, but that's because, so I've drawn it differently, okay. If you draw this as ij, okay, then increasing I goes down the page. So we're going to talk about our neighbors. So your neighbor I plus 1 is down. So in the horizontal direction, your up is right and down is left, and in the vertical direction, up is down and down is up. People get incredibly confused. Okay, drawing things as matrices, I think, is, and these aren't matrices either. These are images. They're not matrices. They're images. Okay, they're not a matrix. A matrix is a matrix. This is an image. It's a 2D array. So actually, if you can draw things, you can draw this the other way if you want. Okay, but people get very confused because I going down, increasing I being down the page. People get really confused about up and down and left and right, and their codes go wrong. So I prefer to draw it like this. But you can draw it any way you want. So yeah, well, this is like, you know, it's like science. Okay, if you draw f of x, y, okay, everyone would draw x going along and y going up. Yeah, complex plane, x plus iy, f of it. Anyone in maths and science and engineering would draw a function with two indices. As the first index goes along, the second index goes up. Okay, x, y. That's what you do. So this is like a function. You know, it's not a matrix. I mean, I don't want to go on, but 2D arrays are not matrices. You know, this isn't. This is, in fact, if I were an image processing guy, I would say that I goes along and J goes down. Image processing people talk about scan lines. So for an image processing person, I should go along and J should go down. That's how. That's how, if you do X Windows programming, okay, I goes along and J goes down. Okay, which really confuses me. But anyway, that's how image processing people think of it. How you draw them is how you want to think of them. And I think thinking them as grid references, coordinates, X, Y. 99.9% in science and engineering, a 2D array represents a coordinate system where X goes along and Y goes up. So that's why. But you can draw it how you like. Okay, I know people don't like this, but you can draw it how you like. So I'll move on. So in the case study, I provide you with detailed printed instructions, a tarball, and I think I give, you know, if in the extended version of this course, I'd ask you to write the serial code. I think I give you a serial code, but I will just briefly, this doesn't work, and I've got instructions on the, so if you look on the, what I will do is I will basically, if it's okay if I go over just by 5 minutes, 5-10 minutes, to basically just give you, so I will now, so there is on the website, you should see exercise material. We have a lot of stuff here, but we have case study exercise sheet, which I will kick up, and the case study source code where I will, I will copy the case study copy link. Okay. So what I will do now is I will go through now, and I'm just going to walk you through this, but basically the case study goes through things in much more gory detail. It goes through the method again. It has a picture of Mel Gibson. Now, actually, this is something very interesting. I give you I/O. Viewing the edges, I'll come back to that. And I give you pseudocode, which, if you follow the pseudocode, will allow you to do the exercise. But you can look at the example, talk about testing it, and then I talk about the initial parallel. The initial parallelization, what I want you to do is to do independent reconstructions. The initial parallelization, so I'll give you a serial code, or you can write your own. The initial parallelization splits the image up amongst processes, does an individual image reconstruction, and then gathers it back. So that checks that your algorithm is correct and that you're doing your I/O, your gathering, your scatter correct, but it doesn't do halo swapping. What do you think you see if you? This is why I think visual debugging. If I run this program, I do an image reconstruction, but I don't do halo swapping. So I distribute the image, each process does an image reconstruction, and then I come back and I display, what do I see? What do you think I see? I don't want to guess. Artifacts, exactly. And so you'll see horizontal or vertical lines exactly where the process boundaries are. And then when you do halo swapping, you get rid of those lines. So that's exactly why I think this is interesting. When I did this, I thought I made a mistake, because if you zoom in, can people see that? Can people see, what do they see on the? So what I did is I did an edge detection on Mel Gibson, and I saw that thing on the right. What does that not look weird to people? Can people see something there? So what they No, it turns out you get nice image reconstruction. So to answer Christoph, it turns out you actually get, I can do this, we can do this. You see quite nice image reconstructions, but they will diffuse, but they don't diffuse very far. Yeah, they don't diffuse far. They diffuse a few pixels. So you're absolutely right. The artifacts do diffuse into the domains, but because the edge detection is local, so Stephanie, what do you mean by halos? I think you've got the right answer, but what do you see? Are you going a bit like that? Won't let you go any further than that. Do you mean the little squares? Is that what you mean? Okay, yes. So no, these little squares exist in this image. They're just hard to see. Okay. So this image, which I just downloaded off the web, and maybe didn't ask for copyright. There you go. I just found it lying around on the web. I downloaded it. I did an edge detection on it, and this image includes, in fact, you can maybe just about see, includes all these artifacts. Okay. Any idea why? Someone, I didn't know. Someone explains. Absolutely. So what compression? So this images are typically use JPEG. JPEG is a Fourier transform based method. You Fourier transform the image, you throw away the high frequencies, which is noise, and then you go back. But these Fourier transforms are done on little blocks. Okay, they're done on little blocks. So the image is split into little blocks. On each little block, sorry, you're not seeing that one. On each little block, you do a Fourier transform and throw away some of the data. That gives you edge artifacts whenever you have on your blocks. So these are JPEG compression artifacts, which you can see. And the block is probably 32 by 30 or 16 by 16. I can't remember which. But this is actually showing, and that's just interesting. It shows up JPEG artifacts, which is quite interesting. Maybe it wasn't a very high quality algorithm. I'm not go back to 100%. So, and then there's lots of other stuff here and other things. So what I'll do before I basically, you'll see if you go to the website, I will now log on to ARCHER2 and just see what we can get. Let's show you. I'm getting my password wrong. Give me 1 second. Okay, I can't quite remember my password, so I'll just use my own account. Sorry about that. So I'll just show you how this works. Profile, presentation. And I'm getting myself very confused. I'm having to use Chrome and just 2 browsers. It is confusing my little brain. So can you? So I'm on. Can you see that? Can you? Hopefully you can see my screen. Yeah, fine. So I'm just going to get that was just the URL, which is on the website. And now we do tar xvf mpp case study. So all I give you is some IO routines which read and write images. Don't look at these. Well, you can. I mean, they just okay. They work. And some edge files. Actually, if you look on the website, you will see that I have actually given you case study solutions in serial in parallel. Okay. But what I will do is I will just show you some of these images, and we can come back to that. So it's explained on the website. But to display these images, you do module load image magic, and the program is called PGM display. Let's look at Edge 192. Right. This will take, so I'll copy that. Oops, sorry about that. I was copying and I missed. So that takes a long time because it should work. It takes a very long time. Okay, something's going wrong. Okay, I hope that. Yes, it's taking a very long time, but it does because it's exporting the display from my. So what I will do is I'll show you what that image looks like. So that is, and that's sort of a Loch Ness monster. That one, that's an interesting one. The other one is I think it's Edge. I like. So this will take a long time, just because, especially if you're not in Europe, if you're not in the UK, but it will. Okay, there we go. So let's have. Is this working now? I'm going to have to stop with a share application. So these images you should be able to reconstruct. That's my favorite one. Anyone think what that's going to be when it's reconstructed? Anyone want to? Yes, of what? Of an MRI scan. It is an MRI scan, actually. Of what? Anyone? What it looks like? Yes, it's actually my brain. I don't know if you can recognize it, but I was a control subject for a study somebody was doing. So that's actually my brain. Hopefully it's normal, relatively normal. But let's just what I will do. We'll have a longer coffee break. Is I will basically show you. Let's go back. I'll just show you what you should get, because I give you the serial code, so I should probably show you what the serial code does. So if you're seeing this again, okay. So what I will do is I will grab the serial solutions, case study solution serial. Okay. Case serial. MPP case solutions. That's going to Fortran 1 OPF serial. So in there's a. I've given you there's the edge one. So actually, the make file may not be correct. Let's have a look. So that is actually compiled for another machine. I have to do that with make /image. But it says, okay, it's processing. It's hard coded to process the 192/128 image. Does 1500 iterations. It reads and it writes. So now if we do PGM display, so this is the this was that Loch Ness monster picture. It's surprisingly, I mean, it is surprising how this algorithm does actually work. So if we so you can see it, but I only did how many iterations? I do 1500. You can see that it's not. I mean, I think Christoph was talking about diffusion error. You can see that the image isn't perfect. It's still a bit fuzzy. But what I can do is I can just run for more iterations. So if it's very simple code. If I kill the PGM display and do image.f90, it's a very simple piece of code, but I have everything hard coded. Let's do 15,000 iterations, not 1500. Okay, so I'm doing 10 times as many iterations. Okay. if you look now, you'll see it's much better. It's a much clearer image, and I think it's probably, now you can actually quantify how good the image is. It's in one of the extra exercises. You can compute a delta value. You can compute a difference between. You can compute an error value, and you can give a quantitative. And you're trying to solve ground squared image equals edge. How different are they? And you can quantify that if you want to. So that's basically enough to sort of introduce the case study. I think probably what we should do is let's take a break, half-hour break. And then lecture will begin at 11:50 in 30 minutes. And you're welcome to, the idea is that over the break, you have a coffee break, or maybe think about this example. But I thought, rather than have you doing this example and having to wait to hear the next lecture, I would complete the lecture material, and then you can go on and we can do this example afterwards. Are there any questions? There'll be plenty of time for questions afterwards, but I overran very slightly there. But I think the quiz, we had a lot of discussion in the quiz, which was very useful. Okay, so let us the tips and tricks lecture is sort of a whole bunch of stuff, which is just useful stuff, which you might find useful. I hope from experience on. So I'll take a break now and start again then. Okay.